So this won't be an example. All we're going to do in this video is collect some results. These results shouldn't be at all surprising. You use them when you took single variable calculus of a real variable, and the results are just, oh, hey, the same thing is true for complex numbers. So the first one is that complex polynomial functions are continuous on all of C, so they're continuous everywhere. And the proof of that is very simple. You consider a polynomial and it's continuous if and only if the limit as z goes to z naught of p of z is p of z naught. So you have to compute the limit of this guy as z approaches z naught. And we actually looked at the limits of these power functions already, and we saw that, well, it was the same as just plugging in z naught. And we also looked at what happened to sums. This breaks down under sum, and the constant multiples come out. So if you sit here and you apply our limit rules, what you'll find is that you do in fact get this. This is true. So this is sort of moral homework. And a proof is in your book if you don't want to do that. And since quotients of continuous functions remain continuous, we also know that rational functions, which are quotients of polynomials, so p of x over q of x, are continuous on their domain. What's their domain? Well, it's the places where the denominator is not 0. So that's the domain D is the z's in C such that q of z is not 0. And then last result I want to collect, just so we have it at our disposal, is the extreme value theorem. So the theorem goes like this. If a function f is continuous on a closed and bounded region, these are the analogs of intervals. Well, the connected version of these are the analogs of intervals for real numbers. What do we learn if this is true? Well, in real numbers, what you looked for were maximum and minima, or extreme values. In complex numbers, the same is true. So f is bounded. And recall, bounded from the book just means that the size of f is less than or equal to a fixed number for all z in the region. So again, this is an analog of what happens for real numbers, and this is a general phenomenon. If you take a topology course, you figure out how this generalizes, but you can think about this guy as the extreme value theorem in this course. All right, so I just wanted to collect those 3 results.